Hello, I'm Grant Bartley. You're listening to the Philosophy Now radio show, and tonight we're going to be talking about quantum metaphysics. I'm from Philosophy Now magazine, and I'm talking to Manjit Kumar, who's written the book Quantum, about the history of quantum mechanics, and we're going to be talking about what the implication that the new physics has for how we're to think about the world and our place in it. Now, the book Quantum Mechanics I found to be an understandable, humane introduction in terms of thinking about not only the physics but also the relationship between the people and what caused them to come to the conclusions that they did. What would you say about your book, Manjit? I mean, how would you describe it?
Oh, that's a sneaky question, Grant.
Yeah.
First of all, let me say thanks for inviting me.
Yeah.
It's a pleasure to be here. How would I describe my book?
Yeah.
Well, there's loads of wonderful books out there about quantum physics,
right,
and especially about the weirdness of quantum physics.
Right.
And what sort of, motivated me.
What's special about your book? I could say, but I want you to say.
To write the book was that I wanted to try and tell us the story, the quantum story.
Isn't it?
Yeah, it's a narrative. It's a wonderful narrative with some wonderfully interesting people that, the likes of Albert Einstein and, the things you hear of Schrödinger's cat, Erwin Schrödinger, the uncertainty principle, Werner Heisenberg. And I just wanted to tell a story of, where the quantum came from, how it was discovered.
The story behind the physics.
The story behind the physics, yeah.
Right.
A combination
and
of
I think you do that admirably well. You tell the drama of the story, not only the ideas themselves, but, you piece it together historically, which is nice. So it's how it all came together in a historical way. So it's as if, we didn't know, we were at the state of ignorance that they were before, they discovered the things. As the thing goes on.
Yeah, I try and tell the story as it unfolded.
Yeah, that's the one. Okay, so I guess the first question I should really properly ask you is, what is quantum physics and why is it interesting or important? What's radical about the quantum way of looking at the world as opposed to the everyday of looking at the world that we have? That's a nice, easy question to start with, isn't it? Yeah.
Starting as you mean to go on.
That's right, yeah.
Quantum physics, at one level, quantum physics is very straightforward. Quantum physics is the label for physics of the atom and the subatomic.
The really small things,
yeah. It's the physics of, the atom and subatomic. Why is it revolutionary or why is it different? Is obviously the quantum, which we'll talk a bit more about in a little bit, was discovered in 1900.
Right.
So, can I just stop you there for a second? What is subatomic? What do we mean by subatomic?
This is Rose Neller, who will be providing our musical entertainment and representing Joe Public as well.
Well, we talk about 1900 here, right into the beginning of the 20th century. There was still a big debate about whether atoms existed or not. And some very prominent and influential physicists and chemists were involved in that debate all the way into the end of the 19th century. Yeah. So there were those who believed in atoms, and the electron. Right, which is
the orbit in the atom,
a particle smaller than atoms, found in atoms, was only discovered in the late 1890s. So when you talk about subatomic, you're talking about
smaller than atomic, tiny. What everything physical is made of, and smaller, if that makes sense. But the question again is, what is different about the quantum way of looking at the world as opposed to everyday physical way of looking at the world?
Well, the quantum was discovered in 1900, right? And it was discovered by a guy called Max Planck.
All right.
I'm not going to get into the details of its discovery, but what he, the idea he had to accept was that energy, was emitted and absorbed in bits, in packets, in chunks.
As opposed to what?
As opposed to the sort of the 19th century idea, the idea that what we could now call as classical physics, where energy was a continuous thing. It's a bit like water flowing through a stream, It didn't come in bits, didn't come in chunks, didn't come in packets, didn't come in quanta. Yeah. And that was the idea that Planck was forced to sort of accept and entertain, right? So energy wasn't this sort of smoothly flowing thing like water from a tap.
Yeah.
But
it came in lumps.
Or
so-called lumps, I suppose.
So quanta are little packets of energy.
Okay.
Well, that's how quantum physics first emerged.
Yeah, quanta, I think, means packet, doesn't it, in Greek? Let me sort of bring out this idea first. What are the one or two findings from quantum physics which you think everybody listening should know about?
Well, the first idea of quantum physics is this idea that there are certain things that in the real world
In the
everyday world, sorry, I shouldn't say real world, in our everyday world, are continuous properties you'd think of. You think that going from A to C means you'd have to go through, B.
Right.
But in the quantum world, a particle can be A, and it can be at C without ever having passed anywhere in between.
So it can sort of teleport itself from one place to another without any intervening
all those
existence.
Out there, yes. I mean,
that's quite weird, isn't it?
That's a different thing that you can't do in the sort of everyday world.
On the everyday scale of things.
On the everyday scale,
because it only applies to the really small scale.
To the really small scale. But the quantum physics, the idea of the quantum, that was 1900, and then the idea was developed and played with, and it was a real struggle to understand the physics that came out of that.
Yeah.
And we can look at that a bit later on.
Oh yeah, we will.
But,
I'm sure.
You asked, you asked the idea about why is the quantum important, or quantum physics. Well, somebody else asked me this recently, and I was sort of struggling to explain it a little bit beyond sort of bringing in, it's responsible for mobile phones and the plasma screens, and there's most of the modern world that we take for granted wouldn't exist in the way it exists. We'd be living in some alternate reality if it hadn't been for the discovery of the quantum and the development of quantum mechanics. So we'd be living in some sort of 1920s still.
Sure, but I'm interested in the philosophical implications of it. So why is it important from, let's say, how we're going to look at how the world is or the nature of reality?
Well, this comes out in part of the debate between the physicists as they developed and tried to understand what they were trying to do.
Okay.
So maybe we can...
I was going to ask you, can you give us just a very short history of quantum physics as it leads to the weird stuff, maybe just a couple of minutes.
Yeah, I mean, okay, just very, very briefly, a very potted sort of history. Quantum, as I said, was discovered in 1900. It was discovered by a chap called Max Planck. He was 42 years old. He was a German professor of physics.
Oh, they're mostly German, aren't they?
They're mostly German. But Germans in the late 1890s had for a long time been experimenting with high-tech ovens. Right. Now, you might think high-tech ovens, right? Because in the 1890s, it was a very dynamic period in physics. You had the discovery of the electron, X-rays and radioactivity. Yet some of Germany's finest experimentalists were working with high-tech ovens because they were trying to heat these ovens up, and they were trying to measure the radiation that would accumulate inside these sort of these ovens, because what they wanted to try and do was to come up with a formula that would help to make better light bulbs. Right. Okay. And this idea of a perfect oven, a black body, was like a benchmark against which they could calibrate light bulbs, because what you want in a light bulb is as much light as possible, but as little heat as possible. So these ovens were going to help them try to come up with an equation that was going to allow them to calibrate light bulbs.
You mentioned black body. What is a black body?
Oh, black body is just... Look, we all know about an iron in the fire. We put an iron poker in the fire. As the temperature, as it gets hot up, you initially find that, you can't really touch the poker. Then it starts to glow a dull red, a bright red, and then it goes for the various colours of the spectrum as it gets hotter and more intense. So what these physicists were trying to do was trying to work out what's the relationship between the colour of the poker, the light it was emitting, the temperature of the poker, and the intensity of the light that was being emitted. Now, it seems like quite a simple problem, but they even wanted to simplify it even further. Right? And this is why they came up with this concept of a black body, which would be a perfect absorber and emitter of radiation. Right. And they could replicate that in the lab by high-tech ovens, if you like.
So because it's perfect, because it's a perfect absorber and emitter, they can make really precise measurements of the relationship between the heat and the colour of the radiation.
Yes, right, especially as their measuring instruments and devices improved. And it's supposed to have been this sort of idealisation. So it wasn't a real light bulb, if you like. It was this sort of thing that allowed them to come up with a perfect curve against which they could measure other stuff. And these measurements... These measurements led to some data, and Planck tried to come up with an equation that would recreate the curves that these guys were plotting from the data that they collected. Right? And he realised he had this equation, and then he had spent 6 weeks working out the physics behind this equation. Right? And when he did that, and he called it the 6 most strenuous weeks of his life, he decided that his equation would only work if energy was being absorbed and emitted by the walls of these high-tech ovens in packets. Right. He didn't like it.
No, because they all thought it was waves until that time. They all thought it was
continuous waves, Yeah. And he thought it would come out in the wash, but they wanted the equation to work. And so, Planck said later we'd have to learn to live with it. But he took a long time to try to learn to live with the quantum, Right. So the idea was just it comes in packets, and that was the discovery. And it came out of practical concerns. Nobody was looking for some revolutionary new physics. It just popped out of Planck's attempts to explain some experiments that were being conducted that seemed a million miles away from the frontier of theoretical physics, if you like, you know.
All right, so that was really how it the whole idea of the quanta was introduced, and I think we're going to have a song now, and then we're going to get into some of the implications of this whole idea of quantum physics and what it means philosophically. All right, well, we've got Rosanella in the studio with us. She's going to sing us a couple of songs, and the first song is called
A Dozen Credit Cards.
A Dozen Credit Cards, and here we go, Rosanella.
Thank you. Thank you, Grant, for having me on your show.
Oh, my pleasure. Oh, thanks, Rosanna. That was great. You're listening to the Philosophy Now radio show. I'm Grant Bartley from Philosophy Now magazine. That was Rosanella with a dozen credit cards. I'm talking to Manjit Kumar about quantum physics. He written the book Quantum, which is the history of quantum physics and the science of it all mingled together. And Alan is the sound engineer, and we've got Marcus in the studio too. Right.
Alan of ASAPEurope.com.
Well done, well plugged. Right. We've talked a bit about the introduction of the idea of the quantum. Now, know in your book that Einstein looms large in the history of quantum physics. Where, he's like the world famous physicist. Where does he come into the quantum story, and what was his major contributions, if you like?
Well, Einstein, Planck discovers the quantum accidentally in 1900, and in my book, the opening chapter is about Planck, and he's called the reluctant revolutionary.
Right.
Yeah? Because, like I say, in 1940, he was 42 when he discovered...
Because he doesn't like the implications of what he finds, does he?
He doesn't even like the fact that, energy comes up sliced and diced in chunks, He's introduced it as a mathematical sort of convenience. He doesn't think there's any reality behind this mathematical idea.
Yeah, that's Planck,
That's Planck. And he publishes a paper, and, distinguished physicists left, right and centre look at the work, and no one picks up on the quantum idea in Planck's work.
Right.
Okay? It's Einstein, when he sees it in 1901, 1902, right, that steps back. And he later says it was a bit like having the rug pulled from under his feet.
Yeah.
Now, in 1901, 1902, Einstein's 22, 23. He's not at some university. He's on the verge of just beginning to work at the Bern patent office, and he spends most of his day, examining patents, looking for weaknesses, right? And but he spends his spare time working in physics, and he's read Planck's paper, and what he begins to do is starts thinking about what Planck has tried to do, in the derivation of this formula called the black-body radiation formula. Doesn't like what Planck's done, thinks Planck sort of jumped a few steps, fudged a few bits and pieces. So Einstein comes up with Planck's formula, rederives it, but he rederives it on the basis that he's treating the radiation in these boxes as if they're like particles, like a gas. And gas back then, even now, but that people accepted that it was made up of particles. Those people who believed in the kinetic theory of gases. So Einstein comes up with a formula that Planck comes up with, but he's come up with it by treating light if it's made up of particles. Right,
and he got the Nobel Prize for that, did he not?
Well, interesting. So Einstein calls this, the quantum theory of light, the one and only revolutionary piece of physics that he ever did. Now, we know this man. He did special relativity, general relativity, and a whole host of other things, but the one thing he himself regarded as revolutionary was this idea that particles, that light could also be made up of particles. Right. Now, in 1905, when he comes up with this idea, for over 100 years, everybody has accepted that light is made up of waves.
And in fact, they turn out to be both, don't they? That's the real thing about quantum physics for me, and I think a lot of people listening to this will think, there's waves and particles. How could light be a wave and a particle at the same time?
Well, just to scroll back for a second on Einstein, he comes up with this theory in 1905, and for nearly 20 years, he's pretty much one of, two people who believes in the quantum theory of light.
Right. Everybody else still thinks it's waves.
Everybody else still thinks it's waves, and Einstein's done something quite nice in sort of coming up with this idea which can explain one or two things, including the photoelectric effect, right, about how electrons are emitted from metal surfaces. That Einstein's explained that. But, he's got a formula that explains some of these results, but they don't like the idea of of the quantum theory of light, particles of light.
That's because they've already proved its waves, isn't it?
That's because they've already proved its wave, and it was about 1924, when experiments were done in America, where a chap was firing X-rays, which are really high energy light waves that we can't see,
electromagnetic waves,
and firing them at electrons, and finding that what he saw was like if two billiard balls had been colliding.
So the light was being scattered as if it was a ball hitting another ball, basically. So it must be a particle.
And that got Arthur Compton a Nobel Prize for that contribution. So and all of a sudden, overnight virtually,
Nobel Prizes here.
Overnight virtually, people began to accept the quantum theory of light.
Right.
Yeah. And what then happened, a year or so later, a French French prince, who was also a German duke, right, Louis de Broglie, he thinks, okay, well, if waves, light waves, can sometimes behave as if they're particles, maybe particles like electrons can sometimes behave as they're like waves.
So we're talking about the ordinary stuff of matter, like the physical stuff we're made of, can not only be particles but can also be waves. Now, this is where the becomes philosophically interesting to me, because I'm thinking, how could a solid particle thing be a wave at the same time?
Well, so by mid-1925, around then, people now began to talk about wave-particle duality.
Right, okay.
And it was a struggle trying to get a handle on it. Right, and there was jokes like an electron on a Monday and a Tuesday and a Wednesday was a particle, and on a Thursday and a Friday and a Saturday it was a wave, and it took Sunday off.
Yeah,
and wavicles. People came up with the idea. Maybe we could call them wavicles or something.
Well, yeah, I like the term quantum, but
one of the people who was struggling with these ideas was Niels Bohr,
right,
who's the third great quantum pioneer. If we start with Planck and go to Einstein, it's Niels Bohr.
Yeah.
And Niels Bohr
he's Danish, Bohr, guys.
And Bohr had made his name by introducing quantum ideas into the atom.
Right.
Yeah. And do you want to go into the atom? Or not?
I want to go into the implications of this stuff. I mean, it's like when is say an electron a wave, and when is it a particle?
Okay. So this is Bohr, right? So what Bohr had done, very briefly, he'd introduced the quantum idea to the atom by explaining how electrons could jump from one energy level to another energy level by emitting or absorbing light.
And that's
particles
how
of light.
We get
quanta.
radiation that we see as light is by these electrons jumping from higher energy to lower orbitals around what they call.
And he's the guy who came up with the idea of energy levels within an atom. He'd sort of quantized the atom. But by the mid-1920s, Bohr is a big figure.
Yeah.
He's a major player.
He's discovered the structure of the atom, basically.
The atom. And by the mid-20s, he's got an institute in Copenhagen where some of the most talented, brilliant young physicists are hanging about.
Yeah.
And one of them is Werner Heisenberg, for example. Another one is Wolfgang Pauli. And Bohr is struggling with this idea of wave-particle duality. So he comes up with this concept. And he comes up with this concept in about 1927 when he's off skiing in Norway.
Yeah.
He comes up with this idea of complementarity.
Which means what?
Which means that for Bohr, the way he explained it, if you like, is that nature will give you the answer depending upon the question you ask. Right? So
you have to explain that.
Yeah. So, for example, the question being, if you do an experiment on light, and that experiment is asking wave questions,
like
the behaviour.
If you do an experiment expecting to discover a wave, you'll discover a wave.
You'll discover a wave.
So this is, and what similarly for particles, if you do an experiment that's going to give you particles, you'll get particles. But what I'm asking really is, what are the difference between the two experiments? I mean, what sort of experiment do you do to get a wave?
Well, for example, the famous experiment is called Young's two-slit experiment.
Yeah.
Right? It's not that difficult to visualise. Imagine you have a screen and it has two slits in it, and behind that screen, you've got a light. So the light is shining on a screen with two holes in it, which now become a bit like two headlights on the front of a car or something.
Yeah.
Each of those, if you like, is now shining a beam of light onto another screen. Now, where those two beams cross, you'll get this sort of series of patterns on the screen.
You get a wave interference pattern.
You get an interference pattern, and it'll be light and dark patches. And the idea is that where you get the light patches is where, sort of two peaks or two troughs sort of, meet up, and they sort of reinforce each other. And where they get the dark bits is where they cancel out. So a trough meets a peak. So they sort of cancel out. And you can see this sometimes in water waves. When it's sort of, two waves overlap, it becomes a bigger wave, or they sort of cancel out and have a bit of storm.
Basically, you're seeing wave effects from these beams of light. Yeah.
Because he would say that experiment is a wave experiment. And what we get is the wave phenomena that you see of interference. And stuff,
so that's fine. So when is it a particle then?
Well, when Einstein comes up with the quantum theory of light, one of the things he can explain is a thing called the photoelectric effect. And this effect had stumped everybody. Imagine you've got a piece of metal, now, and you shone a beam of light on it. Now, people had expected that electrons would be emitted from the surface because light energy was hitting the metal surface. So they thought that the greater the intensity of light that was hitting the metal surface, the greater would be the energy of the electrons that came off the surface. But what they found, in fact, was the energy of the electrons that were being emitted by the surface didn't vary depending upon the intensity, but where it was the number. Now, if you look at Einstein's quantum theory of light, in a more intense beam of light, you have more light particles packed in there. So the greater the intensity, the greater the number of light particles, the greater the number of light particles hitting the metal surface. So the more electrons you're getting coming off. Right?
So it's not...
So are they actually bouncing back, these electrons?
Well, electrons absorb the energy that's being shined onto the metal surface. They get the energy and they can sort of escape from the metal surface. Yeah.
So it's basically the more light you shine on, the more light you get bouncing back?
No, the more light you shine on the metal surface,
Yeah.
that beam, if you thought of it being made of particles of light, would now have more particles of light in a more intense beam.
Yeah.
They individually, if you like, would hit more individual electrons.
Right.
They would absorb the energy from those light particles, and more of them would leave the metal surface. Classically, pre-Einstein, pre the quantum theory of light, people were expecting a more intense beam of light meant more energy, meant more electrons with more energy being given off. Not the same number.
Not more electrons, but like more energetic electrons.
Exactly right.
That's the difference.
So, yeah, that's right. So here, you couldn't explain that with the wave theory of light, for example.
Right.
Now, Bohr would say
this photoelectric effect thing
is a particle experiment, and you're getting particle answers back from the wave theory of light. And the other experiment,
the
two
beams of light thing,
is a wave experiment, and you're getting wave phenomena. Right, so this is how he tried to sort of square the circle.
So this is basically, we've just talked about two different experiments where you get two different types of thing for one of these wave particles, like a photon.
I mean, for Bohr, you shouldn't have an experiment where you get both things happening.
Why can't? But okay, let me go back a bit. Why can't a wave be a particle at the same time? What's wrong with that idea? Is that just
You're asking a $64,000 sort of question. Yeah. You know, look, people have sort of pondered these things, yeah. But in experiment after experiment, one aspect or another manifests itself.
So basically, you're saying you never get both aspects in the same experiment.
Well, not as far as anybody has done it. Yeah. So that's one of the ways he came up with the concept of complementarity, because he was looking at the phenomena, right? He was looking at the experimental data and the experiments around him, and he thought, hey, how can you sort of square this concept of wave-particle duality? And he came up with this idea of complementarity. For him, that sort of explained it.
So we cannot have a particle and a wave at the same time. We have to have them separately. So we're going to have a wave experience and a particle.
Well, a way of thinking about it would be, for example, like an electron. Everybody thinks of an electron as a little billiard ball particle.
Yeah,
right?
This is what I'm going to ask. But anyway,
so there's loads of experiments in which that's how they behave. They behave like particles, yeah?
Right.
But we've all heard of electron microscopes, you know, those wonderful images that you can get right down, like these alien landscapes they sort of reveal, you know, much more detail than sort of an ordinary light microscope. And that works because of the wave nature of the electron is being exploited in that technology. Right? Yeah.
And it wouldn't work unless they were waves. Yeah.
Do you know what I mean? Yeah. But so he's saying that it's not, you know, rather than think of an electron as a particle or as a wave, depends upon the experiment.
It depends what you're doing with it.
And, you know, we can't help but we all, you know, sit in this studio. We can't help thinking of the electron as these tiny little billiard balls, or the proton as a billiard ball.
Yeah? Well, no, this is what brings me on to this question, right? I mean, I think probably most people still think of atoms as like you've got one lump in the centre and then you've got these electrons spinning around it like as if they were little planets or something, yeah? But I'm sure quantum mechanics has a different view of what the atom is like. This is what this guy Bohr discovered, this different structure of the atom. Now, if it's not like a little solar system, what is an atom like? On a quantum mechanical view.
You're now trying to make it difficult for me, aren't you?
Well, you know, this is, you know, these are the interesting questions, aren't they? The difficult ones are the interesting ones.
Okay, so if you go through 1900,
right?
Well, no, at the end of the 1890s, people are debating the question of whether atoms exist or not, and most people at that time think, a bit like the Greeks, take a lump of matter, keep on chopping it up, and you can't chop it anymore.
Right.
Yeah, I think you'll tell me that.
Yeah, that's atomist. That's Leucippus and Democritus. Anyway.
That's right. Indivisible, isn't it? The whole idea of where atom comes from.
Yeah, that's.
But by the 1890s, the end of the 1890s, people have discovered J.J. Thomson at Cambridge has discovered the electron.
Right. So here's this wave particle. One of these wave particle thingies.
You've got an electron, and then you haven't. Then we start looking at the structure of the atom. People are working on what are atoms, and by 1911, 1913. You know, Ernest Rutherford at Manchester has come up with a model of the atom, the one we all grew up learning in school.
The solar system.
The solar system one with the nucleus at the middle,
which is wrong, by the way, everybody.
With the electrons circling the nucleus like the planets around the sun.
Yeah.
Now, the problem with that,
granted
work. It was wrong, and it doesn't work. Absolutely right. It doesn't work because if you replace the sun by a nucleus, the positive bit of the atom, and replace the planets by electrons, right, which are negatively charged, if they go round in a circle,
like a planet,
Electromagnetism says that a charged particle will radiate energy.
Right.
So as they go around in a circle, they're radiating energy, and their orbit, if you like, decays, and they collapse into the nucleus. A bit like one of those Earth satellites whose orbit decays over time, and it falls in, crashes back into the Pacific or somewhere like that.
It would be just like a big dynamo, a tiny dynamo radiating energy all the
right.
time. Yeah,
that's right. And it would collapse within the blink of an atom would collapse within a fraction of a second.
So it can't work. This idea can't work.
It can't work. Bohr, the Great Dane, who comes up with the principle of complementarity, set up the Institute in Copenhagen. In 1912, 1913, he's working on these ideas of how to fix Rutherford's atom. And he comes up with this idea, and he basically says there are certain orbits in an atom in which an electron can occupy, and it won't radiate that energy away.
Yeah,
so it's a fix.
Only very certain numbers
and the
of
quantum idea he introduces into the atom is that only certain energy levels
orbits,
energy levels that electrons can occupy exist. Only certain ones exist with an atom. An electron
that are stable.
That are stable. The electron can't just be anywhere it likes.
Yeah, it can only be in a stable orbit. Yeah,
that works.
Yeah, right.
For a bit.
Okay, for a bit. Okay,
because it works for the hydrogen atom very, very well.
Right,
in
which
terms
is very simple. Hydrogen atom being just one proton with one electron going around it,
and it works really, really well. And it sort of explains the experimental data that people had accumulated over decades for it. But when you get to more complicated atoms,
like anything else,
it didn't quite work as well. Right?
Yeah.
And so by the mid-1920s, that sort of picture has been replaced, because by the mid-1920s, 1925, 26, we have the emergence of quantum mechanics.
Right.
Okay? Because prior to that, from 1900 to the mid-20s, quantum ideas, the quantum concept, the idea that things like energy came in bits.
Yeah.
And later, things like angular momentum was also sliced and diced in atoms.
I'm not even going to go there.
Yeah. Think of momentum and think of something going around in a circle,
Yeah. Like a skater.
Yeah, a bit like a skater, absolutely. Yes,
but it only comes in bits anyway.
Yeah. But there are other things that are discontinuous, yeah? So the quantum idea has spread.
Right.
But the way what people have done nearly, for the first sort of quarter of a century is taken classical physics and bolted quantum ideas here and there to try and solve problems that they've been confronted with.
Right.
There's no sort of overall logical or overarching structure like you have with Newtonian or classical physics. Everybody, I'm sure, is aware that
there's no underlying theory behind it.
Yeah, Newton sort of managed to sort of bring some order to classical physics by having his three laws of motion.
Yeah,
that managed to embrace quite a lot of phenomena that you could quite explain it. Same thing with his law of gravitation. There was nothing like that for quantum mechanics, and the desire was to try and come up with a quantum mechanics that did for the atomic and the subatomic
world. A basic set of equations, what explains it all.
Yeah, that what Newton had done for classical physics, they were looking for a theory that could do that for the quantum domain and the subatomic. Okay. And that is quantum mechanics. Right. Now, in 1926, 25, instead of one quantum mechanics,
a whole bunch of them.
There's two.
Right,
and one was formulated by Werner Heisenberg, and it was called matrix mechanics. Now, the only thing you need to know about that, it just used arrays of numbers.
Nothing to do with Neo.
Yeah, but matrices were just arrays of numbers, and he was able to manipulate these arrays of numbers to come up with measurable things like the energy of an electron and things like that. And
it's a really complicated.
It's a complicated sort of idea, but it was using mathematics that most people weren't familiar with.
Yeah.
These days, matrices are taught at GCSE level, sometimes A level, certainly. But back in the 1920s, physicists were unfamiliar with matrices,
right?
And even Heisenberg.
So nobody liked it. So this brings in
Erwin Schrödinger.
Right. I'm glad it's not just me.
Yeah. Because what happened with Heisenberg, even though when that theory was developed, it produced the right results, most physicists found it very difficult to work with and visualise things with.
And these are physicists we're talking about.
And bright, some of the brightest.
Nobel Prize-winning physicists couldn't use his matrices.
Erwin Schrödinger comes up with what's called as wave mechanics,
which is easy,
which is much easier. Right. Even though it's still complicated, but it's much easier because it used equations and mathematics that physicists grew up with. They used these differential equations.
Like an equation describing a wave, basically.
Absolutely. And people from who were tutored from using 19th century physics, they felt much more comfortable. It was easier to work with in most instances.
Right.
And so there were these two sort of rival camps until people came along and showed that they, in fact, were two different mathematical formulations of the same thing. The physics, underlying physics was exactly the same.
But you still haven't answered my question, which is...
So we come up with quantum mechanics,
Right.
And Schrödinger, right, because we talked about wave-particle duality before.
Right.
So there's this new idea that emerges. Just think of the hydrogen atom.
Right.
Think of the nucleus.
A proton.
With the electron going around it.
With one electron going around it.
Okay. Now, Bohr had just prescribed this.
Yeah.
And he sort of calculated.
Said, this is how it is.
This is how it is, but why?
Nobody knew why.
Now, using the idea of wave-particle duality and the fact that an electron could be a wave,
right,
the orbits that the electron could have in the hydrogen atom,
right,
were ones in which you could get a whole number of wavelengths fitted in. Because if you imagine some sort of a ring,
right?
Yeah, sort of a round ring, but in that ring you can only get so many wavelengths.
Whole number of wavelengths.
So that the beginning joins the end.
Yeah.
Rather than overlaps, and so that's what and that's what meant that these were the
wavelengths. Come on, let's get back. A wavelength is what though? What is it? It's like the distance between two.
Yeah, it's the distance between two troughs or two peaks. It's one complete cycle, if you like. And so red light and blue light and yellow light, all these ones will have characteristic wavelengths. The distances vary between one, say, fixed point and its repeat.
Yeah.
In a cycle.
So you can only get whole numbers of those in your electron orbits.
Yeah. This is what sort of this idea when you start talking about wave-particle duality and electrons being waves as well. So there seemed to be a natural way of trying to describe these orbits. Yeah,
and this isn't even the complicated stuff.
This is not the complicated stuff. when Schrödinger comes along, right, these electron waves, if you like. Now you have to start thinking. We're thinking flat at the moment, aren't we? We're thinking sort of pancake stuff.
Yeah,
really.
right, okay.
Now we have to start thinking in 3 dimensions
because we've got complicated atoms.
Because
now,
what happens
with lots
now,
of electrons.
Because the word we've both tried to stay away with from quantum mechanics is probability.
Oh right.
Yes.
Yeah. Right. We've stuck away from probability. But Schrödinger comes up. There was not just Schrödinger, but the easy way of looking at it, if at one level, is that an electron in an atom. Mm-hmm. All you can do is work out the probability of where it might be.
So it's not in a definite place.
It's not in a definite place.
It's just you can give a probability of it being in one place rather than another.
That's right.
And you can describe a different set of probabilities.
Yes. And then you get these sort of 3-dimensional sort of what they call orbitals and stuff, where it's more likely to be and less likely to be. And
but if it isn't definitely in one place, where is it?
Well, a good question. I mean, now you get into the nuts and bolts of something, the Copenhagen interpretation.
Yeah, okay, this Copenhagen thing, which is Bohr's interpretation of quantum mechanics. What is it? In a very sort of quick style.
Well, okay, the Copenhagen. We've already touched on one aspect of the Copenhagen interpretation: wave-particle duality.
Right.
The idea of complementarity.
Right.
That something like the electron will behave as a particle or as a wave, depending upon the experiment you ask.
Right.
Right.
Okay.
Yeah?
We got
you conduct.
that.
So that's one aspect of it. The other aspect of the Copenhagen interpretation was the uncertainty principle.
Yeah.
Right. And it was the uncertainty principle was formulated by Heisenberg in 1927, or discovered, whichever way you like to do it. And Heisenberg said, look, previously in classical physics, in everyday world, we can pinpoint with 100% accuracy the position and the velocity of a particle or an object.
Right.
Yeah.
That's the normal world, but in the quantum world, it's not like that.
It's not like that. He was saying that, look, the more you know about the position of a particle, the less you know about the momentum or the velocity of the particle.
And that's mathematically provable.
And there's mathematical stuff, that shows all these, the limits to which you can prove both.
Right.
So the more you know about one, the less you know about the other. To the extent where if you know precisely where an electron is, say, in an atom, you know nothing about how fast it's going or its momentum.
Yeah.
Right. The more you know about its momentum,
which means
the less
it doesn't
you know
have one, according to this Copenhagen.
The Copenhagen.
Right?
So for Bohr and Heisenberg, who supported his position, they began to think, well, hang on, an electron. They decided, this is their interpretation, that an electron doesn't have a position until you do an experiment to measure its position. And you conduct, and you do an observation or a measurement. They call it that. Observing or measuring, and design something to measure its position. It doesn't have one,
which is crazy.
But that doesn't mean we cannot actually calculate the position of an electron. We can only assume it might be in a certain position.
There's one thing that's worth clarifying slightly. We sort of skated over it a little bit. The mathematics of quantum mechanics, right? No one sort of debates the the correctness of the mathematics.
Yeah, it all works, doesn't it?
It all works, and as we talked about right at the very top of the show here, there's loads of stuff in the studio that works because quantum mechanics works.
Right.
The problem is the question of interpretation. What does it mean? What is it saying? Yeah. So when Bohr and Heisenberg are trying to work out what it's all about, they come up with this idea that there is no electron, right, with a position, and you do an experiment to measure its position. Right? Quantum mechanics can give you probabilities. That if you do, an experiment, this is the probability you might find an electron here.
This is the philosophically interesting thing now, isn't it? How can you observe something or do a measurement on something that doesn't exist? Surely you've got to say something like, it exists in, a state of probability or something like that.
Well, yeah, I
right?
mean, people do talk about, the Copenhagen people talk about, an experiment to measure, say, the position of an electron in the hydrogen atom, right? It has these probabilities of where it could be, or these potentialities, if you like, of where it could be, these superpositions of all the different possibilities. When you actually measure it, they sort of collapse into a definite position.
Because you know where it is, because you've measured it.
Yeah. But if you do that 100% with 100% accuracy, rather than saying, it's 80%, I think it's there, then you don't know enough about its momentum.
Yeah,
right?
Which means it doesn't have one definite.
So this is so this is where Einstein and Bohr and their great debate sort of begins,
right?
Around these sorts of issues.
Yeah, right. And we're sort of coming near to the end of the show, so we can't go into this really. But just a couple of minutes, and
so Bohr, Heisenberg, the Copenhagen position is fundamentally, you create, if you like, or bring into being an aspect of reality like the position of an electron when you conduct some measurement of it. Prior to that.
So we're bringing into being physical reality by observing it.
Yeah, because there's this whole, it gets really, really more complicated. What's a measurement? What constitutes a measurement, for example? Some people say it has to be done with a large-scale piece of classical equipment. Yeah. But hey, look, this desk here is all made up of electrons. Where is that sort of border? So, but Einstein was like, hang on, there's an independent reality, that's his take, that exists out there, and it's the job of science, physicists to try to work out and uncover and discover that reality.
Ah, okay. Well, Rosanella's going to sing us another song now, while you all try and work out what the hell that means. And what's the next song called, Rosanella?
The next song is about time. In fact,
well,
it's called Old Time. The first song had more politics and environmental issues that we cannot solve with all the plastic cards, credit cards we have. And this one is about time that we try to conquer, since we're talking about quantum. Just a quick check that it only works. This song is about time. Time that we try to conquer. Time that we try to defeat. But time conquers us. Time, you've been running all night. No time. Am I just passing by here? Am I just spending time here? Am I just spending time here? I'm not sure where I'm going, just another place lost in space. I'm not sure where I'm going, just a few light years away. Kings and monarchs, popes and ayatollahs too, so they could conquer the world, fooling themselves, thinking they conquer all, thinking they conquer all. But in actual fact, you time you are invincible. But in actual fact, they conquer no.
time. You conquer us, oh, oh. You're invincible, oh, time. Am I just passing by here? Am I just stopping by here? Look at those faces. They lost all the traces of wisdom long gone, long lost and gone. Under the surgical knife, under the surgical knife. But in natural fact, they're just skin and bones sewn up together. But in natural fact, you can only take our minds back. But in actual fact, oh time, oh time, you conquer us, oh, oh, invincible, oh, time. But in natural fact, they're just skin and bones sewn up together. But in actual fact, we can only take our minds back. But in actual fact, oh time, oh time, you conquer us, oh, oh. Invincible, oh, invincible, oh, yeah.
Thank you very much.
Thanks, Rosanella. That was time. And it's nearly time for the end of the show. So I feel like we've just really started getting into it, but I hope you listening have sort of just at least got some idea of the sort of paradoxical or problematic nature of quantum physics. I'm Grant Bartley from the Philosophy Now magazine, and I'm talking to Manjit Kumar, who's written Quantum, which is the history of this quantum physics that you've been hearing about. Now, I've just got to ask a couple of non-related, different sorts of questions. So who's your favourite figure from the history of the development of quantum theory, and why?
Okay, well, I'm going to cheat on this one.
Yeah?
Because it's called Quantum,
Right.
my book,
Right.
but the subtitle is The Einstein, Bohr and the Great Debate About the Nature of Reality.
Uh-huh.
So instead of one, I think my two favourite characters are Einstein and Bohr.
Oh, no, that's cheating.
No,
I gotta make you choose one rather than another.
Why both?
I'll do your desert island disc thing.
I tell you why I like both.
Yeah, that's right.
I tell you why I like both. Because actually, from 1927 to 1955, when Einstein died,
Right.
they conducted a debate about the nature of quantum reality.
Right.
99% of the time in friendly terms. It wasn't acrimonious. There were times when Einstein didn't really want to see Bohr in the 1940s, we want to replay the same arguments again.
Yeah.
But 1962, right, the night before Bohr died and Einstein had been dead for 7 years, he was drawing out a thought experiment that him and Einstein had discussed in 1930.
So they still hadn't, at their deaths, they still hadn't resolved what they think about quantum reality.
So for me, these guys, both of them, I think, are actually very important central figures. Einstein, because he wanted to know if the moon exists when you don't look at it.
Right.
And he believed it did.
Well, yeah.
Bohr, in a sense, said no.
So, but again, how does it come into existence? But we won't get into that. Maybe if we get another chance, we'll go into the philosophy a bit more. But about Niels Bohr, who's the other guy debating with Einstein here, he constructed the modern picture of the atom. He laid the foundations of modern chemistry, because it's all about how the electrons behave around the atom. And, and in doing so, he explained the periodic table of the elements and why they're all laid out the way they are. he's such much a genius as Einstein, isn't he? Why isn't he as well known as Einstein, do you think?
Well, I think in Britain, and probably in places like America, he isn't as well known as Einstein, but I'm sure back home in Denmark he is.
Yeah, right.
But you've got to remember also about Einstein's fame. Einstein becomes world famous in 1919, right, when a British expedition goes to test out one of his predictions from the general theory of relativity, which is that light is bent.
Right.
Right, yeah?
Because of gravity.
By a gravitational field. So they take some photographic plates during a total eclipse of the stars that, behind the sun, and they compare them to the stars 6 months earlier. And then all of a sudden Einstein is, front page news around the world, because one of the people he's overtaken is Newton, the great British scientific hero, because he's talking about gravity. So Einstein is world famous from 1919 onwards, and he has the hair, and he's got the persona, he's got the charm, he's got the wit, and so part of that contributes. It's a shame that Bohr isn't as widely known as Einstein.
But as you say, probably in Copenhagen, they probably big him up a bit more than Einstein there. Well, unfortunately, we're sort of running near the end of the show, so we can't really go into it anymore. But I just want to ask you, what if people are interested in this sort of things? What other events or stuff have you got coming up, Manjit, that they might come?
Well, I was going to say, like we talked about at the very beginning of the programme. I mean, my book Quantum is a narrative.
Yeah,
and there are plenty of.
It goes into all the detail that anybody would want, I should say.
But it's a combination of the people and the physics, and there's loads of wonderful other books out there that also just cover the weirdness of quantum mechanics. Yeah, like Marcus Chown's Why Quantum Theory Can't Hurt You, as an example of one. And Marcus and I are doing a talk together in September at the Royal Institution, where people can come along.
Where's that?
That's in Piccadilly, the Royal Institution.
Right, okay.
Yeah, and so that's sort of a joint event.
That's September.
That's kind of nice to look forward to. And I'm interviewing John D. Barrow at the Earls Court Festival on the 6th of July. Okay. John Barrow is a cosmologist at Cambridge, and is one of Britain's leading cosmologists, and he's brought out a new book called The Book of the Universes.
All right.
When he, beginning with Einstein's
lots of them.
There's loads and loads of them, more than you can shake a stick at. He starts off with general relativity, and the idea of the Big Bang, and he looks at the different ideas that have come about in the last sort of 100 years.
So
cosmology.
Where would that be, and what date is it again?
It's on the 6th of July. It's the
Earls Court Festival. www.earlscorefestival.com.
And it's at the Prince of Tech.
At the Prince of Tech.
And I think it starts at 7:30.
It does indeed begin at 7:30 until 9 p.m. July the 6th.
Yeah, so everything from the beginnings of the Big Bang, or was there even a pre-Big Bang, to the whole idea of the multiverse John will be discussing.
Okay, partly the reason why we're doing this talk now is in conjunction with this talk that you're doing at the Earls Court Festival. I think Rosanella wants to say just a little bit about what that's about.
Yes, I'm here singing a couple of songs. Thank you, Grant, for having me again. But I'm a bit of a representative, a volunteer of the Earls Court Festival, and this team is Kaleidoscope. And please do go to www.earlscorefestival.co.uk. It has already started. In fact, it was launched on June the 19th and is going to end on July the 17th with a street fair. There are going to be over 40 events for children of every age. So literary event, book launches, music, lots of music, etc., etc. So go and see it. We don't have time to go into it, but www.earlscorefestival.co.uk.
Okay, thank you. Okay, so Manjit's book again is called Quantum. My book is called The Meta Revolution, and the next show of the Philosophy Now radio show will be on the 13th of July, and I'll be talking to Ray Tallis about his book Aping Mankind. Okay, see you next show.